Hi everyone, thanks for watching my presentation which is about variational inference with mixture model approximation for applications in robotics. For various applications, roboticists may want to represent or learn distributions of robot configurations. The configuration of a robotic manipulator is often defined by its joint angles, and maybe the transformation of its floating base as well. The configuration space might not be the most obvious and simple choice to represent distributions or constraints. Often, it is easier and more elegant to define the distribution under several task spaces. For example, a Gaussian distribution can indicate preferred position of the end effector. Obstacle avoidance can be defined as a distribution over distances from objects. In this work, we propose to use the product of experts as a framework to fuse together these different distributions as a distribution over robot configurations. A product of experts is a model where we multiply several densities which are called experts together and renormalizing the product. Each expert can be defined on a transformation of the data, which are in our case, the different task spaces. There are a few things that we may want to do from this density. One is to draw samples of configurations. Another is to estimate the normalizing constant of the distribution and its gradient, which is necessary if we want to learn this distribution by maximum likelihood from a dataset. Let's take a two-dimensional problem for illustration. This is a 2D planar robot and we defined a target distribution of end effector as a degenerated Gaussian. It defines a line constraint. In a 2D case, we can evaluate the product of expert density on a grid and display it as a color map. A classical method to sample from an unnormalized density is to use Markov chain Monte Carlo. A walker is moving around randomly, following rules which makes him visit states with high probability more often. However, these techniques are known not to scale well in high-dimensional space, especially with highly correlated distributions like this one. They also have troubles with multimodal distributions. Variational inference is an alternative based on optimization. The idea is to approximate the product of experts with a tractable distribution, which it is easy to sample from and is properly normalized. The optimization seeks to minimize the reverse KL divergence between the product of expert and this approximate, which can be done using stochastic gradient descent. We propose to use a mixture model as an expressive distribution to approximate our product of experts. A mixture is built by summing the probability of several simple models. As component distributions, we can choose Gaussians with a full covariance matrix or more complex distribution like bananas, which are Gaussians through a differentiable mapping. They are particularly convenient to represent inverse kinematic solutions which are highly correlated. With this approach, it is also possible to set up a hierarchy between the tasks. Let's take the example of a bimanual planar robot where each end effector should follow a different Gaussian distribution. If the two objectives are not reachable, the resulting distribution tries to accommodate both and converges in the middle. It is possible to prioritize one objective by filtering the gradient of the secondary objective such that it does not influence the resolution of the other. This is made possible by the fact that stochastic variational inference does not need to evaluate the unnormalized density but only its gradient. This characteristic is shared with only a few Monte Carlo methods. Here is an example with a humanoid robot, where we have a distribution for each foot, for one hand and for the center of mass. On left, there is no hierarchy, resulting in the robot to lose balance. On right, the center of mass has the highest priority. As experiments, we evaluated the quality of the approximation of the product of experts on different tasks, with a different number of components and family of distributions. For example, we considered the problem of approximating the distribution of configuration of this 7-degree of freedom manipulator, where the end effector follows a given Gaussian distribution. With one Gaussian component, the results are poor and do not exhibit many variations. Results improve with more components and banana-shaped distributions. A much richer variety of solutions can be retrieved. In ongoing work, we investigate the use of the proposed variational approximation in order to learn the parameters of the product of experts from data. For example, we are considering a case where the robot has a tool attached at the end effector, with an unknown position. Given samples of configurations where the new end effector follows a Gaussian distribution, we would like to retrieve the transformation of the tool and the track distribution. Our model should be as well able to generalize to new target distributions. We are comparing against other more general methods for learning conditional distribution like variational autoencoders. These techniques are more general but do not exploit the structure of the data as well, which results in poorer generalization. In this work, we propose to use the product of expert as a framework to represent distributions of robotic configurations. We also proposed an alternative to sampling techniques to approximate this distribution. The approximation can be as precise as sampling alternatives by augmenting the number of mixture components. Variational inference has some very interesting advantages of sampling methods that are presented with more detail in the paper. Most notably, they enable the extension to a prioritized formulation. The coverage of a distribution is also easier to assess, which is of interest with sampling-based motion planners. Codes are made available on this link. They allow researchers to build upon the method and use it with other robots, by providing a URDF file.